welcome to the Efficiency Gains Through Automation and Innovation session. I'm Jordan Oxford, the session chair. Next speaker is Will Hunt, presenting on how to use Heave, 3D movement, and ore block optimization to increase grade and dilution. Will started his professional career as a combat engineer in the Marine Corps, and he moved on to civil construction, owning a heavy highway development and mining company for over 10 years. He started consulting in blast movement and blast engineering and OreControl in 2012, and this led him to the founding of OreControl Blasting Consultants to focus on ore control innovations through empirical and analytical approaches. Will holds a Bachelor of Science degree from the Colorado School of Mines, where he returns as a guest lecturer and teaches short courses.
Okay, thanks for attending the talk. What I'm going to discuss is a new tool that we've created to optimize ore control in 3D. And it's going to consider heave, blast movement, and the goals of the operation. I'll apologize in advance for my voice, getting it back after a couple weeks. So I want to acknowledge my partner, David LaRosa, who's actually in the room as well. And David is the principal for CRC Ore and has been the principal for Metso, BMT, and he actually invented the BMM system that we use to gather a lot of movement data around the world. So just for starters, what is blast movement? Why do we really even care about it? Blast movement is the movement of the rock caused by the fracturing of the rock. So if you can find energy in a rock mass and detonate it, you're going to move it. It's going to move sometimes a little bit, sometimes a whole lot. It tends to move differentially, and you can see in this image here. Is there a pointer up here somewhere by chance? Yes. Cool. There's some water. Just a little. That won't help me. But thank you. Okay, so you can see in this image, this is a real blast. You can see differential movement at depth throughout the blast. And we see that all over the world. Again, to a greater or lesser degree, depending on the magnitude of that energy. So there's a lot of case studies out there. I've published a bunch, Dave's published a bunch, and various other people have published a bunch. And they show that movement really is valuable to understand. But it's what we do with the movement that's really critical, and that's what we've created a tool to manage. So the last part about this is that the heave, what we found is actually the heave and the vertical movement and the differential movement can be just as important, if not more important, than just the magnitude of horizontal magnitude of displacement that we see. So pretty much around the world until recently, until maybe 6 months ago, ore control was really treated as a 2D problem, even though it's a 3D problem. So it tends to get quite complicated when we put things into 3D, so to simplify it, ore control geologists have tended to work in 2D. And this is a paper from 2011, APCOM. There's actually a couple papers here from 2011. So the way the industry has always treated blast movement until recently was to essentially take a usually unoptimized polygon that is hand-drawn by a geologist and slide it horizontally based upon the moved or the magnitude of the blast movement that's been measured. So we just take a polygon and we slide it. And here's some other examples. We just take a polygon and we slide it without respect for that differential movement or the heave or how it's going to be dug, even though at the same time we know that we've got this going on. So this is a vertical cross section, and each of these points were blast movement monitors that were dropped this deep and traveled this far. So we know we got differential movement. We know that the top and the bottom don't act the same, that we've got sometimes a trend line that we can see. I think this has stopped working. We've got a trend line that we can see. So what do we do about that? This is what always vexed us. And just to illustrate it, I want to show you a real blast. So for scale, look over on the right side on top of the pile and you'll see how small the people are. So this is a really complex situation to try to manage in 3D. And at this particular operation, it's structurally controlled narrow vein gold. And the gold is vertically dipping. And I'm going to show you some cross sections of this mine in just a bit, but that 90-degree dipping structure doesn't exist anymore. So if we've got a heave pile that looks something like that, and the measured movement underneath it looks like this. So a lot of movement in this blast, of course, about 26 meters in the bottom, but what do you do with that? How do you control ore when you've got a vein that maybe takes that shape? It's pretty difficult to deal with. And this is something, again, that vexed us. So at that same operation, we've monitored a whole lot of blasts. They've used BMMs for many, many years. And where that guy is standing, we dropped 2 BMMs, and these are manufactured by BMT. They're just transmitters. We dropped 2 underneath them in a dedicated hole, 5-meter bench, and they were 2 meters apart. The top one moved way up there where that yellow ball is. There. And the bottom moved down here. 90-degree narrow dipping structure. So I'm going to show you what that looks like in cross-section. This is what we have in situ. They mined this in 2 flitches. Up at the top, you can see I've got an in-situ OreControl polygon. Again, rarely optimized. Very, very few people even try to optimize in 2D, especially because of this problem. So we've got the ore has traveled according to those measured vectors that you see. So we've got a structure that looks something like that in the post-blast. We've got a lot more data in it, but this particular hole, I wanted to show you what was going on. So because of poor energy confinement, if anybody happened to go to my paper yesterday, I talked about blasting and bench height optimization. Because of poor energy confinement, they really struggled to break the floor. So we've got a structure that looks like this in the post-blast. Now how do we mine it? What do we do about it? What the industry has always done, and it was because it was the best way that we knew to deal with it. We didn't have a better solution. We've taken an in-situ grade control polygon and slid it horizontally. And then we project it to the surface, we walk over the surface and place flags. Now let's just make the assumption that they can dig vertically, 90 degrees. They usually can't, but let's make that assumption. That's what we're actually mining, which means that's our ore loss and dilution. Okay, now let's just say, well, that's 2 flitches. What happens if we did it 1 flitch? We take that in-situ grade control polygon, green one, we slide it with the blast movement measured to the blue, project it to the surface, and then mine it. In this particular mine, we measured 60-degree working face angle. So that means that's what the shovel is actually digging. Now, if I want to get all the ore, that's what I have to do. By the time I do that, is it actually ore, or have I diluted it? Now, I asked this question at mines. I've consulted now to probably 75 different mines, and my partner as well, probably the same amount or more. And I get different answers. It's a rhetorical question. It is billions of calculations to be able to determine what is optimal in that location. And if I mine from a different direction, I get a completely different result. So how the shovel attacks the pile matters. How we flitch it matters. The heave that we use matters. So should we mine it like that? Or just keep the original slid in situ polygons and just forget about how it's going to be mined? It's a difficult problem. So to answer that, and we recognize it has to be a practical answer, we created OreControl optimization software, and it's called OrePro 3D. We've got a booth upstairs if you want to talk to us about it, 634, I think. But we call it OrePro 3D. This is what it looks like. And the inputs for this software are your in-situ grade control model. So the assumptions we're going to make in determining what to do are that your in-situ grade control model is right. And if it's wrong, please work on it. It needs to be right. You can keep the highest resolution that you feel comfortable with. So you don't have to aggregate together into massive blocks for an SMU. How do you take a big block and move that block differentially? You don't. You take lots of little blocks. So you keep that high resolution that you have, and you move that differentially. Okay, now if you measure your blast movement, BMMs, polypipe, whatever you use, great. If you don't, we can help you. We take your in-situ grade control model, your blast design, and whatever movement data you have, and your post-blast surface. And that post-blast surface is really important because that's going to tell us a lot about the movement. It's going to tell us a lot about the vector field. And it's going to tell us a lot about how we need to handle the heave and how we're going to slice it if we're going to do flitches. The output is constructed with a 3D vector field, and it's a post-blast grade control model. Now, most people don't ever take that out of the software because our brains are incapable of optimizing even in 2D, much less 3D. But we manage this problem, and we give you optimized OreControl polygons for whatever your considerations are, whether it's geochemistry, grade, subclassifications, and this whole process takes about 3 to 5 minutes. So it's really, really quick. So I want to show you a couple case studies so that you understand the implications of this, the value proposition that we're talking about. First one is a 5-meter bench, structurally controlled gold. Early on, by the way, most of our customers were gold, just so happens. And one that I have to shout out to is Kinross, who who gave us a lot of assistance in building this, purpose-built with them, and a lot of funding. So a lot of our early case studies were gold, but at this point we've worked in iron ore, zinc, copper, lead, I'm forgetting some, silver, PGMs, lots of places. The industry's accepted this very strongly. So the first case study is gold, 5-meter bench, 2 flitches. They used BMMs to get accurate measurements. The difference between their horizontally slid grade control polygons and the optimized polygons, $77,000 after cost. So that's after the cost of process. And you can see over on the right, I know that the writing's kind of small. For each, what we would call a layer, so it would be like your polygons on your top flitch, your polygons on your bottom flitch, we give you the grade, tons, volume, the dollars that are inside of those polygons, as well as the recovered dollars, and then the net. And the net's a really important one. The net is the money contained in that polygon less the cost to process it. And this is so you can make a decision on which mining direction is best. And I'll go through that in the last case study. But we also give you the ore loss, which is ore you can't get because it's economic. It's uneconomic to get it outside of those structures. And then dilution that you must take because it's economic. Case in point, something that is really super high grade, but your minimum polygon size is quite large. It still can be economic to eat some dilution in order to get that really high grade stuff. And vice versa. You might have a pod of high grade, but by the time you mine a polygon around it, your minimum polygon size, it's uneconomic. So we give you all that data for each layer. Case study 2 is a 10-meter bench with 2 flitches, $137,000 after cost. And I can go through these with anybody that wants to afterwards. Case study 3, $138,000. Now, anybody that happened to have gone by our booth has seen that we've had blasts that are $600,000-$700,000 in value between what the mine was doing in situ, sliding polygons horizontally, and then optimized 3D. So even in 2D, human beings are not capable of optimizing polygons. Now, there are some 2D optimizers out there, but they don't manage the heave, they don't manage the differential movement. It's essentially the same process, move something horizontally. So that's the third case study. Now I want to talk about mining direction and why the next case study is included here. So if I give you these 2 scenarios, I'm pretty sure everybody in this room would tell me the one on the right is the best one for geology and for OreControl, because you can essentially clean off that contact, right? But you can't really do it with the one on the left. But if I was to mine the one on the right from the other direction using the exact same grade control flags, I would miss most of that structure. So I have a customer just a few days ago that was telling us about a large loss they incurred with a shallow dipping structure that was mined in the wrong direction. Even though they had the optimized polygons, the polygons were optimized for a certain dig direction, and that's what we do. So if they laid out their polygons and the operation went from a completely different direction than they expected, and they ate a lot of dilution. That happens. I showed you a cross-section why that's an issue. So it's important that you communicate with your operational staff, and if you're going to have trouble holding a dig direction, you can assume a 90-degree working face and eat a bit of dilution on either side, or you can flitch mine. That's another option. And I talk about that actually about half an hour after this one lets out in another room. So anyhow, that mining direction does matter, and here's a case study to illustrate that. This is narrow vein gold. This is 10-meter bench, 1 flitch, so bulk mining methods. Okay? The difference between their slid polygons, their horizontally slid polygons, and the optimized polygons is $120,000 to $266,000, depending on which direction they attack. But depending on which direction they attack, they get $225,000 more gold with optimized polygons. So the digging direction in this is worth nearly $250,000. I was at an operation where the geology department had always tried to get the mining department in line to mine in this direction. They wanted to mine in this direction, just like the picture I showed you here. They said, we want to do what's on the right. And operations fought them. So we ran this exercise, and they demonstrated to the operational department why it was really valuable for them to mine in the appropriate direction. And The conversation lasted about 10 seconds, and they said, okay. But without that ammunition, it just wouldn't have happened. Okay, some questions that the software can answer. Just showed you which is the best mining direction. What's the penalty for digging in a different direction than optimal? So I get into that in my next paper, to Flitch or not to Flitch. But in a single blast, over in that paper, something like $130,000 by laying out polygons and going in a different direction. That's just one blast, one day. Makes a big difference. Is there any benefit to mining flitches? There can be. In most cases, and I've done this probably 50 or 60 blasts at this point, in most cases, you can get just about the same value mining a single flitch or multi-flitches. Everybody knows what I mean by flitches, right? Slices. You can get just about the same value if you can control the dig direction. If you cannot control the dig direction, flitching can help. Okay, especially in these narrow vein, shallow dipping structures. So it's a way to mitigate operational difficulty with the dig direction. Is my equipment properly sized? So one example that we've had, we looked at two different equipment sizes for the same blast. One was a 5x5 minimum polygon size, another was a 20x20. So big bulk equipment versus selective equipment. And the difference in that one blast for that mine was 23,000 tons of dilution. They would save just by using this equipment instead of that equipment. So it enables an operational decision. Should we blast towards a choked or free face? If you blast towards a free face, we have a certain blast dynamic where the bottom is moving considerably, and we're taking a structure that might look like this and turning it into this. If we blast towards a choke phase, we're actually turning it that way. So the result is different, and the result is different depending on how you're going to mine it. So you can run that analysis. Which direction should I blast? Those are some exercises we run through. And then we calculate the post-blast tons and grade for any shape. So if you have a polygon, we've calculated the swell, because remember, one of our inputs is that post-blast topo. So we calculate the swell, and we give you a post-blast density for that rock. And so you know what you're mining and where you're sending it, which according to our customers has been a serious value add. So just summarizing all this, rarely do people ever optimize their polygons in situ, but even if they do, they're kind of missing the point. Because we have heave to deal with, we have differential movement, we have blast movement in general, we have mining direction, and those are considerations you just can't deal with when you take a 3D problem and you slap a 2D solution onto it. So a human being cannot perform it. It's billions of calculations, but we've been quite creative, and we figured out ways to do this entire process in 3 to 5 minutes. So optimized ore control and grade control is done post-blast, not pre-blast. Keep your planning. Pre-blast planning is great, but what is achievable pre-blast is not always achievable post-blast. And that's where the ore control and grade control should be done. So thanks again for attending the talk. If you have any questions, I'll take them. I know I couldn't have been that thorough. Well, thanks very much. I appreciate your time.
That's the question in the back.
Sorry? Okay, does size and shape of the blast matter? For us, it doesn't matter. For you who are blasting it, it does. The smaller the blast, the more chaotic that blast tends to be, and the more edges you tend to have. We can deal with whatever you throw at us, but from an ore control standpoint or grade control, the ideal situation is bigger blasts with more consistent movement. So I had a paper yesterday where we looked at bench height and what the resulting impact to ore control is based upon that bench height. So if you have really short benches, really small blast, you try to blast a couple rows at a time, you have a lot of chaos, and you're not actually peeling layers away the way you think you are. So did I answer your question to that? Thank you. Yes, sir. Benjamin. Thank you.
I've seen a picture of from shovel excavator. Do you take into consideration the kind of equipment is used? Because I see some mines open that you do loaders,
Sure.
which are big buckets instead
Sure.
of narrow buckets.
We do. So as an input into the software per blast, this essentially processes ore per blast. As an input are a couple things. One, the essentially selective mining unit that you want to use. What is the minimum polygon width and the minimum polygon length in the travel direction of the equipment? Okay. If you're going to use, let's say, backhoes and sit on the pile and excavate, then you can assume a 90-degree face if you're doing really short flitches. So that mining face angle is a consideration. I don't give you that per equipment because it really depends on your geology. From what I've measured, really short flitches, so I'm talking like, 3 to 5 meters at most, you can sometimes get 90 degrees if you're using backhoes. But on big benches, it's a lot more. So 60 to 70 degrees is typical, but it really just depends on the geology. So you may even have in one pit 60 degrees in this area and 70 degrees over here. It's an input for you. And it's, we know that it varies as the shovel is digging, so it's an approximation. But the difference with a 60-degree mining face angle, toe to crest, on some big blasts, I've seen it 15 meters. So it does make a real significant difference what they're aiming at. Thanks for did I answer your question, Benjamin? Thanks. Yes, sir. Absolutely. We interface with all the fleet management systems. Yep. Push it right to them. They'll never know the difference. Except they won't have to do a bunch of exceptions every day when you blast to a free face and their model is an in situ model and it's saying that it's mining something that was mined a month ago. Yeah, so now it's accurate. Did that answer your question? Okay. I think I'm out of time. Thanks very much, everyone.
All right. Our next speaker is Dr. Shahram Tafazoli. Who's presenting on how deep learning will revolutionize blast optimization using artificial intelligence to measure fragmentation in shovel buckets. Shahram is the president and CEO of Motion Metrics International. He founded Motion Metrics in 1999 after earning a PhD from the University of British Columbia in the area of robotics and intelligent systems. He is also an avid inventor holding several patents, an adjunct professor with UBC ECE, an angel investor in several promising Canadian tech startups, and an associate member of the Creative Destruction Lab at the University of Toronto.
All right. Good morning, everyone. Thanks for coming to my talk. Essentially, I will be, let's use that image, shows a hydraulic shovel where it has our camera installed on the stick, which we use for multiple purposes, from missing tooth detection to measuring the size of teeth. But in this particular talk, I'm gonna explain how we are using AI to use that same camera to measure the rock sizes inside the shovel bucket. So this is the agenda for my talk. I'll talk a little bit about the problem of blast optimization, why we need particle size distribution, and how one can analyze it inside the shovel bucket. That's the problem. Then I'll talk a little bit about the solution, how it works, and 3 aspects to using AI here. One is on the embedded system and 2 on the cloud. And finally, I'll show you some exciting field results that are very fresh. I actually went over logs over the last month and extracted these results to show you guys. And these are from 4 different type of shovels: a hydraulic shovel, a pianist shovel, a Bucyrus shovel, and also an excavator. All right, blast optimization. Many of you guys have seen this. Essentially, in an open pit mine, from all the way from drilling to digging and hauling and crushing, conveying and grinding. So a mine-to-mill optimization requires particle size distribution everywhere. But in particular, I'm gonna focus on that part, where you have the shovel digging material, and that's so close to post-blast in order to perform blast optimization. So you have done a blast and you want to get a good idea what the rock sizes are, and you want to improve that blasting. So that's where the focus of my talk is going to be. For everywhere else within my company, Motion Metrics, we are using stereo imaging to do rock analysis everywhere in the form of a industrial Internet of Things. But I won't talk about that in this presentation. So just imagine you got that camera on any, one of these shovels, and these are real images, real logs that I'm presenting here. On the top left, we have a hydraulic face shovel full of material. You see a big rock, almost 1 meter in there, big boulder. On the bottom left is a P&H cable shovel. Again, there's mostly a lot of fines and 2 rocks there. That's the Bucyrus shovel. And on the right-hand side is a hydraulic backhoe. So it's used a lot of those in mines in Australia. So the question is, you got this camera looking at this scene, how do you do the rock sizes and how AI is employed? So what's image? Just very quick basics. Image-based PSD, you capture an image, you delineate the rock boundaries. Either you use humans to do that, or you use conventional image processing algorithms, or as of a couple of years ago, we are using AI for that. So that's the delineating the rock, and then we apply scaling. So essentially, how do you go from pixels to inches, centimeter, meter, to get to what's that particle size distribution? As simple as this, really, there's no more to that. In this particular image, you can see 2 known objects are used for scaling purpose. So if you want to get the physical size of the rock, this is a very simple formula that the scaling factor for a given rock is directly proportional to the distance from camera. So let's say on the image, you have this object, which is 20 pixels, and your scale based on your distance is 1.5 centimeter per pixel. So you just do a simple multiplication and say that object is 30 centimeter. Now, if you had the same object, but the camera was twice farther, then that object would be twice the size, as simple as that. So that's the basics of scaling. This slide is very important. So what are the approaches to scaling? Traditionally, people would put objects with known size in let's say on the face of the mine, take a picture, go back to the office, find the known sizes and do scaling. There's some approximation that works well. Inside the shovel bucket, it's very obvious that if you don't have 3D imaging, the way to go is to use the bucket size, because that's the known size that's happening, which I'm going to explain that. In a conveyor belt, you can assume the camera is at a fixed distance from the material. You can use laser imaging. But what I want to say is that the best way, in my mind, after being exposed to this problem from outside of mining, so I don't have mining background, 0 mining background here, electrical engineering, is to use 3D imaging. So every pixel I'm measuring it in 3D imaging, and then addresses the safety concern. I don't have to go on the site, put things. It's very fast, and I'm not making any assumption about the surface and so forth. So the best way approach is the bottom one, which we are doing in the form of IoT, but I'm not going to explain that. I'm not going to talk about that model, that, or even the amazing 3D imaging. So this is a very simple presentation. You have a simple problem in hand. You have a single camera looking at the bucket. During the digging cycle, 80% of the time you are able to see the rocks. How do you do the rock sizes from that? How do you go from that, focus of this talk, to this? So let's talk about the solution. I really worked hard on this problem with our engineers, and we decided that really we had to break it down to 3 problems. One, on the embedded system, so I have the camera connected to the computer. All I have to do is select a good frame where I have a full bucket where the material is not moving. It's a good candidate for analysis. And I want to do it often enough during the operation of the shovel. So that's number one. That image goes to the cloud. On the embedded system, you don't want to do too much stuff because your processing power is limited. There is environmental conditions. There's a lot of shock and vibration. So we do that number one. And the next 2 steps are on the cloud. On the cloud, first, I have a candidate with full bucket. I will find the bucket in that image to use it for scaling. And second thing, I will find region of that image, which is a very good choice for where I see the material and I want to do the analysis. That's number 2. And the number 3 is, again, on the cloud, I'm going to show you how we use AI to do the segmentation of the rocks close to human performance. So, but the difference is a human may take, a big image can take up to 4 hours to do delineation. The algorithm I'm going to present, it takes less than a second, and in many cases beats even human on the performance. So we're quite excited about that. So these are the 3 steps, and I will quickly go over them. So first, what we do, we have developed tools in-house, and we have humans, intelligent humans, that they look at the images of the bucket, full, empty, and so forth, and they label them with these tools. Where is the material? Where is the bottom of the bucket? Where is the background? Where are the teeth? Is it empty bucket or full bucket? So just imagine thousands of these images labeled, which is supervised deep learning, really. So this is used to train the algorithm. So embedded processing, remember I talked about it, in embedded system, all I need to do is to choose a good image to send it to the cloud. How do we do that? Just imagine this is the input image, which happens to be a full bucket. Look, I have two modules, and they are very fast. One is, look at successive images, something which is called optical flow in image processing, map of the movement of each pixel between two subsequent frames. Essentially, if you have this bucket and the swinging, you have the foreground with full material, which is not moving, and you have the background, which you have a lot of motion. So you get this kind of mapping happening. So that's number one. Number two is uses AI, exactly using the supervised images that I showed earlier, humans have labeled. And I essentially with AI, I can assign in one image, every pixel, I can assign a probability. Is that a good scene for fragmentation or not? So is rocks inside the bucket? I don't want rocks outside of the bucket because I don't know the scale. So an example you see exactly on this image, that's the result of AI. This is embedded AI on the embedded system, which based on probability. So if I get a good chunk of probability and that overlaps with this guy, that's a good example of an image to send to the cloud. So the image on the right-hand side, you can even see the bucket has been delineated. That goes to the cloud. So this is the part has to be very efficient because that embedded computer we are using for missing tools detection, tools for monitoring, and other purposes which are more mission critical. The rock size is not super mission critical. There's only one thing is very mission critical there. Let's see who is awake. Can anybody say what would be very mission critical when it comes to rock sizes? What would you care? What would you see in the scene with rock sizes that would say the operator has to do something different? Any guess? I found this one of the most mission critical things in our challenges is the big rocks, which is called boulder. If I see a boulder in the shovel, I essentially have to detect it within seconds and tell the operator, don't drop it. Because it's bad for the crusher, it's bad for the back of the truck operator, it can damage the equipment, there's many reasons. So, but that's not what I'm covering in this talk. I'm just talking about how do we want to do rock sizes in order to improve blasting. So it's a non-mission critical, so we can do it on the cloud. Let's make the talk a little more fun. So the next steps we actually learn from the industry on AI. So this is called, I'm learning from our AI engineers, by the way, feature map extraction network. Essentially, deep learning networks are used that gets from that high resolution image all the way to the right, different networks that are like Lego pieces in there. Essentially, feature extractor looks at that and says, does that image contain human eyes? Is there nose in there? Or is there lips? And you can see as you go further down to the right, you can see that. And we are solving a similar problem. I have an image. Do I see a bucket in there? Is that a full bucket? Do I see the background? Do I see this and that? So we answer the same question, similar technology, we apply it to mining. So here is on the cloud side. So a good image, good resolution, decent resolution. I wish we had higher resolution image. We don't have it, but we have tons of installation of this system. So we are living with the constraints that exist there. Is on the cloud. We fit almost thousands of rectangles of different sizes and answer two questions. Do I see a bucket inside this? So you can see the probability map. This guy is 90% sees a bucket. And on the right-hand side, do I have good material for fragmentation inside this? When those two overlap, which is the case here, that's a good example for segmentation. So, and I have the bucket size figured out. And this is with AI essentially saying, if the bucket was 5 meters, so use that for scaling problem solved. The next problem we use AI is we minimized, we say maximum number of vertices is 12. Use AI to find out where the region of interest is, where are rocks to be segmented, where you don't see dust, where the image quality is good, where there's no shadow. Shadow is also nasty. So we solve that, and the result is those kind of images. You see, and why do we want not more than 12 vertices? Why not more details? Because if you want human to go and correct it, you don't want to have too many of those edges to be corrected. It just becomes very cumbersome. So these are based on real needs. And didn't get a chance to talk about the AI-based segmentation because we are applying it to the images inside the shovel, portometrics images handheld, belt metrics. So essentially, the idea is we have thousands of images that we have got human labelers to go and label the rocks, and we have used the latest technology in AI, and we have come up with an algorithm which does the same thing as I explained earlier, much, much faster. So essentially, I've challenged our AI team, which we have been working for 5 years on this problem, to say that I want to get similar segmentation as a human would do, but rather than take hours to do it, give me below a second of time with GPU technology and all that. So we have that figured out, and what I'm going to present you is some results here. So this is a hydraulic shovel at an African gold mine. And I think somewhere we have the date here. That's February 24. So that's the image of the bucket. This is the result of AI-based ROI, segmentation, and everything. And you see the P numbers over there on the right-hand side, P80, P100, P50 from this image. And green is like within the range. Yellow is like big size. You see there's a couple of big rocks. P100 is 953 millimeter. So I'm gonna go quicker with these results. So this is same bucket, another image. You see a little slanted. That's AI, artificial intelligence region of interest. That's the segmentation. I'm gonna go back and forth. Did quite a decent job. And honestly, this problem we have been working for 15 years in motion metrics. We use conventional image processing. I've had teams of engineers working on this. Everybody is saying, oh, it's an easy problem. 3 years later, oh, that's so hard. And the algorithm gets bigger, bigger. AI, honestly, I feel like is perfect to solve this problem. In this case, you don't see any big rocks. You see that all green and within range. Another example, again, no big rocks. This is interesting. You see here, you have teeth. Remember I was showing labeling earlier with human labeling? I mean, we have had humans labeling like thousands of teeth. It's important not to include that inside rock fragmentation because it's going to skew the result. Again, another example with a boulder. This is the one, a live boulder detection. If it detects, you say, don't drop it, drop it outside. So that's more than a meter rock. You can see large sizes and so forth. So these are all from the same shovel. And I chose this one because it has lots of finds. It does make mistake. I want to highlight that, so it's not all perfect. Let's see where we have a problem here. Okay, I can see, for example, this is not a real rock. But it's kind of, imagine, so the good thing about machine learning is that anywhere you see a bad performance, you can give it back to humans and say, can you relabel, fix this, and then retrain the algorithm. So the old method, I have a customer, very good customer, Freeport-McMoRan. We have a system and they are not happy with performance. We have to work another 6 months to come up with a better algorithm and improve it. In the new day, when the results are not good, we find the data which is not good, we relabel them, retrain the network. Within a week, we say, we have a new software for you. But really what it is tens of thousands of new coefficients in the same old software. So this is a P&H shovel, which is a copper mine in Chile. Again, AI did a decent job. It's not perfect. On purpose, I chose some results that are not the best as well. You can see this part is missing. The blue area is fines. The rock is nicely segmented. And you can see size-wise, it's saying it's mostly fines. Big rocks, and the green is very small there. This is another one. quite decent. Again, AI did a decent job. Remember, I used that delineation of the bucket to say, this is my scale. Another one, pretty decent. No big sizes. You see all the within the range green. Another one, this is a Bucyrus shovel, another Chilean copper mine. It's pretty good, exactly right in the material. And the final field result, this is from an excavator in Australian gold mine. For example, here it's kind of hard to see the two rocks. AI decided to combine them. Which in reality, I believe they are separate. But you can see you have both big rocks, boulders, some within range, and lots of finds in this image. So it's doing the job. All right, in conclusion, I have 1.5 minutes. So particle size distribution of the material inside shovel bucket is a very good indication of the blasting because it's really the first action after blasting. So combine it with the GPS of the location you're digging that from, and it will give you an idea of how good the blasting was. So we actually, we use AI in almost every step. We use it to select a good full bucket image on the embedded computer with limited resources, send it to the cloud. That's number one. Number two, we find the bucket edges for scaling. We use AI to say, where are the edges? And that was thousands of boxes went around, and on the cloud, you have unlimited resources, chose that. Number three, we delineated where's the region of interest? Where are the best image to do segmentation when you don't have shadow, the quality is good, and the material is not moving? And number four, the most important one is how do I segment that image automatically? In the old algorithm, because we had problem, we developed tools on our online cloud platform so humans can go and correct. But now we are on our way. Still, I think we are not 100% there, but we are on our way to pretty much use AI to do this. It's a very cumbersome job. I've gone to blasting companies when there's a team of 20 people, all they do, they go kind of trace the rocks. So I showed the field results from 4 different type of shovels and excavators. And how do we improve this system performance? Essentially bad data, we relabel them. And since I started giving you this talk, till now, about 100 images from buckets around the world were uploaded to our system. And our guys are watching those closely, and anyone with any of those which is not nicely delineated, they will relabel it for the AI. So, and that would address the big data part of the problem. Thank you very much. Any questions? Yes. Okay, very good question. So what I presented here is 2D. Single camera, a high-res analog camera, because we have had it for years on the shovels. What you are referring to, 3D is the ideal approach. So the 3D sensor I showed you there, if I was today, I want to go to many mining shovels and do this, I would prefer that because the camera is high-res and I am doing 3D measurement. So the part that I use the bucket size for scaling, no more, this is not needed anymore because the sensor is measuring everything is 3D. So what I presented here is 2D, single camera looking at the bucket. And considering the application on the shovels, that's because of how much shock and vibration you get. Practically it's more possible than now to have 2 camera system on that and so forth. But we are looking into 3D in future. Yeah. My ideal is, I tell you, this is the dream I have. Everybody has dreams. Mine relates to rocks. It's funny. I look at every rock as a data object. I want to tell where the location is. I want to say what the size is with high accuracy, and I want to in future say what's the ore percentage, what's the texture, what's the hardness with remote sensors. Because if you know that, you can improve blasting. It's like tons of savings in energy, there's safety concerns, and so forth. So, thanks.
All right, next speaker is Catherine Pena. Her talk is on the drill digitization at Pueblo Viejo. Catherine has a civil engineering degree from Santo Domingo Institute of Technology, where she graduated in 2016. In college, she did a 6 months exchange in Canada, and after graduating was part of the structural reliability of bridges at Santo Domingo project and worked as a construction engineer. Now she's the drill and blast engineer at Pueblo Viejo.
Good morning. Good morning. Can you hear? My name is Catherine Peña. I'm from Barrick Pueblo Viejo, and today we're going to talk about the drill and blast digitalization at Barrick Pueblo Viejo. First, this is a little agenda. We'll see a little overview of our mine and also an overview of the department. We will talk a little bit about our online vibration system, the digitalization of the bench, and the benefits that we've had with these applications. First, we'll see a little site overview. Pueblo Viejo is an operating mine in the center of the Dominican Republic. We're in the province named Sanchez Ramirez. The site consists of 3 pits. We have Moore, Montenegro, and Cumba. We also have 3 limestone quarries. We have Quemados, San Juan, and Las Lagunas. Our processing facilities are found central to the site. Currently, the tailing dam is at the southern end of the mine at around 16 kilometers round trip. We have more than 130,000 tons mined daily, and additionally 30,000 tons of limestone also mined daily. Regarding to our production, we mine around 50 million tons per year. We have an 1.51 waste ore ratio, and we have 1 million gold ounces per year. Regarding to our equipment, we have 34 CAT trucks, 2 Hitachi excavators, 3 loaders, and 5 sand big drills. So why this subject? Basically, in 2018, Barrick had a goal of becoming a leading 21st century company. The mining industry, generally speaking, is one that is resistant to change and slow to generate technological breakthroughs that can lead to industry-wide disruption. We knew we could lead the industry in this space, so we embarked on a journey to transform Barrick into a leading 21st century company. Basically, Barrick saw this tech gap as an opportunity instead of an obstacle, improving the quality and flow of information, enabling our people to make better, faster decisions. On a mine site, those are outcomes worth their weight in gold. So let's talk a little bit about our department. As of 2014, we started using high-precision GPS on drill rigs. We also started our inventory tracking on a digital platform. Then in 2015, we started using a drill penetration rate for blast design. So we categorized hardness types, and with that, we started designing blast with that information. Then at the end of 2015, we started changing paper to digital devices on the field. So that's basically when our digitalization had like the little boom. As of 2017, we started monitoring our KPIs with online dashboards that you can access anytime that you want. We also started monitoring fragmentation with the motion metrics, portal metrics. Then we started using the blast logic system at the beginning of 2018. At the end of 2018 also, we started have digital management of our drill consumables. And right now in 2019, we are starting to use a blast stability index for blast design. And we started using, at the beginning of February, our online vibration monitoring. We also have fragmentation dashboards. Since you know fragmentation is fundamental to mining, this information is highly valuable for the mining area, our tailings storage facility, and our process plant. So basically what we have here is we go take pictures with the portal metrics, as I told you before, and we have our best curves, our worst curves, and average passing. And basically the PAD size and the finds that we have in the mine. Regarding to our online vibration system, it's a simple digital system that uses GPS, GSM technology, and mobile technology. We started on February 2019, as I just told you. And what we want to do with this is we want to generate vibration models and predict the effects of every blast. It also allows analysis and management of stations online. Right here, we are seeing a little map of the mine, and we have both permanent and mobile stations. Basically, we have two on our acid rock drainages, the ones that you see RDN and RD3. We also have spotted with the geotechnical department some places where we can have where we have like faults and where it's important to have those vibration readings. This is the interface. Here we can see where some of the vibrations are located. And this is a little view of how the lectures, the program presents the lectures. With this online vibration system, we basically want to measure far-field vibrations. We want to create reports for the drill and blast department, for the process plant, for the geotech department, for environmental purposes, and also for the government. Also, as I told you before, we want to have predictable models to avoid damage to infrastructures, pits, and walls. Now, focusing on one of the department and company's pillars, digitalization, we've been looking for technology that allows the automation of data generation, supervision, and process innovation. That's where Blast Logic takes place in, being one of the best softwares on the market. Basically, this program allows us to generate back analysis by blast, bench, and pits, and so on, in a timely and friendly manner. Therefore, we can look up for business opportunities and improvements for the drilling and blasting process. This is a little picture of our before and after. Like we usually, as you can see in the pictures, we were really manual department. We had blast hole loaded sheets that had to be completed manually in the field. We also have all this paper with the blast plans, and we basically want to eliminate all that by using our softwares and our tablets that integrates all the information so that it even updates automatically. Like you can be in the field working with deeping with something as simple as just deeping our drill holes, and then in the blink of an eye we can have that information on our office to make good decisions about the blast that we are going to make. Right here we can see pictures of what we can do. Basically, we want to have our post-blast results, comparison between actuals and design data, having more efficient way to input and manage collected data, allowing the prediction of potential risk and operational problems. Also, we have an automated adjusted powder factor based on the hole length. We have friendly and understandable report generation. We have seen an improvement also in the supervision, drilling, and engineering process. And we have a synchronization of the entire drilling and blasting process on one single platform. This streamlines the engineering and operation workflow, basically. Here we can see, as I told you before, we have our auxiliaries that they do a series of measurements with that tablet. We have deep-in entries, we have backfilling entries, and we also have our blast holes. They're being charged automatically into that tablet. So we have all in one system. Here, we can see a little example of what our digitalization of the bench is. On the first one, you can see the powder factor along a whole bench. Then on the second one, we can see a drill error, so that way we can measure how accurate our drills are being. On the third one, we see the deep in error, so we can see the amount that our holes fall after they're being drilled. And we also have a water surface of how was it on the pit. And as you can see, actually, we can have conclusions by seeing this. Between the blast, you can see that we have the less powder factor. That is because there is where the holes are more potentially falling. So with that, we can get into conclusions and work with that in order to not have, for example, boulders, or have a better improved fragmentation, and so on. Some of the reports that we can have with this software are the dependent fallback report. This is a report that tells me how prone are the holes to fall through time. So that way we can estimate what's the perfect time to start a drilling process in order to blast it. Since you all may know, Dominican Republic is we have a lot of rain there. So that's a really important thing that we should know to have a better blasting process. Also, we have reports like a drilling accuracy report, so we can have we can measure how our operators are drilling our patterns. So we can have largest error, our shortest holes, the average drill depth error. So with that, we can make improvements constantly. We're also using dashboards. With these dashboards, you can have like a little summary of how that blast was. Basically, we can have drill depth variation information. We have like hole counts, blast stones, powder factor. We can have also the percentage amount of holes that were charged and which ones were not charged, our short holes, long holes. We can also have water depth, since I told you that it's a really important factor on our drills. We also can have like how our costs vary between actual and planned. We also have the ability to have, as I told you before, by bench or by operator or even by drill, how are our KPIs, basically. So what have we achieved with the whole of this digitalization of the bench? Basically, our drilling accuracy has improved a lot. We have a just-in-time drilling. We have a drilling optimization plan. So we had 6 drillings working, and we were able to stop 1 machine due to the improvements that we could apply after using all of this. We can manage our KPIs by operators, machine, pits, and phases. We can do blasting back analysis and immediately improvement processes. We also have the online management of the drill and blast, and we have cost savings of the explosives and an over-drill control optimization. Actually, our department reduced around 5% the holes that we had to re-drill due to the information that we've started to manage here. And that's basically what we have for today. If you have any questions, go ahead.
Our final presenters today are Bob Riggle and Jason LaForest. Their presentation is on haul truck pass match versus payload targets for loading optimization through technology. Bob has over 40 years of experience in the mining industry. He joined Cat Global Mining in March 2011 and his current role is electric rope shovel and dragline product performance manager. Jason has over 1 year experience at Caterpillar in his leadership development program. He has had roles in continuous improvement and service mining product groups. He holds a Bachelor's of Science in Mine Engineering from Colorado School of Mines.
All right, so we're here to talk about pass match and payload targets, utilizing technology to optimize your loading productivity. Hopefully you're in the right place. Today's challenging mining environment, there's a lot of focus on cost per ton, big data, technology, smart mining, all those buzzwords. So technology is a tool intended to take you to the next level of performance, but it's still a tool that requires the right people and process to receive the benefits, as Clayton was saying earlier. So we're going to look at a couple of best practices, lessons learned from sites we visited, some of the most experienced operations using the latest technologies, but still common opportunities that remain. A few of the things we're going to talk about: prerequisites to benefit from the technology, a few things you want to iron out first, a few of the types of the payload management technology, and how to use the data to drive the right behavior, really just manage the operators and make decisions. So hauling makes up 45%, approaches 45% of your mining cost. The loading drives your productivity. So if you're looking to improve cost per ton, you're getting the right payload on the truck as fast as possible is certainly a good opportunity to look into. Bob will talk a little bit more on quantifying this.
If any of you have seen any of our application presentations in Caterpillar, this chart's been around for a very, very long time. Starts with cycle time, operator efficiency, and payload. But when you look at the improvements on a cost per ton basis, and even most recently just validating with one of our big mining customers, payload still is a huge driver as far as the operation of the trucks. So as we look at how we're going to use technology to manage that, I know we focus a lot on machine life, component wear, and cost per ton, but still the value of all this mining equipment is really in the field and how we use it. So this is kind of a level set where we're coming from.
So next we have a couple of the prerequisites. We're going to talk about cycle time and machine configuration, getting those big areas of your payload and your cycle time ironed out first. We'll have a little background video playing, just going over the proper dig sequence, and also showing an example of double side load-in just to improve that truck exchange time. Some other things you should consider is, does the GT need to be replaced more often, more frequently to improve your penetration rate? Is 4 struck passes faster than 3 heaping passes? Does the loader or shovel wait for the trucks? Can you improve the pre-position for faster exchange times like the video here? Is the face properly blasted for consistent loading, cycle times, and easy digging? Some of these things have a bigger impact on your productivity than you're adding technology at the next level. But the more important thing is that you really, if you're missing 1 or 2 pieces of this puzzle, it'll lead to some inconsistencies that inhibit the technology from indicating and driving the right behavior. The other prerequisite, your machine configuration, getting the right payload. This is a diagram, some unrealized capacity in the traditional rectangular dipper shape. That top area you see doesn't usually get the fill, so if you reallocate that weight, make it a little wider. In the lower area, some areas you can fill, you increase your fill factor, do it faster. It's surprising how many mines we find opportunities from reevaluating their how well their shovel, their dipper, bucket, and truck align with the different fragmentation and the range of densities. So they were engineered, but nobody goes back and looks at it. So it's good to do like a scale study, verify those densities, reconfigure it, look into those things. A few other things you might want to look at: is the bucket or dipper volume constrained or weight constrained? Can you get the right target payload on the truck without spillage? Do you need to increase that volume? Should the different trucks and shovels be allocated to different materials to match the different densities? A couple other considerations that have a bigger impact than adding your technology, things you should do first. So getting into a couple of the types of payload management technology, there's others than just these. There's your material movement tracking, Getting the right material to the right place certainly impacts your cost per ton. You can do preventative condition monitoring. That's also going to increase your uptime, your component lives. That'll help your cost per ton as well. But we're going to talk about some of the ones you can manage. Real-time data systems, the scoreboards on the trucks. On your left here, what you see inside the loading cab unit. The performance trending systems, this is machine data you can download manually, or you can download it remotely over Wi-Fi and track the operator performance and their payload. So you manage what you can measure. The operator assistance systems, they help by guiding the path of the dipper or the bucket, limiting the range so you improve the learning curve, make it more consistent, payloads in between different operators, improve your productivity. Also some secondary benefits of reducing unnecessary wear, boom jacking events, swinging in the bank, hoist stalls, improving that component life really improves your productivity as well. We're going to focus more on the first two, things that you can manage using the data. So getting into an example of the loader operator's role. From their perspective, you already have the engineered solution done. You've configured the machines. Simplified example, 200-ton truck, 50-ton bucket capacity, should be 4 passes. But if you get into material, poorly fragmented, it's no matter how much time you spend in the bank, you're just not going to get more than 90% fill factor. So you add on that technology, the scoreboards or the in-cab real-time data feedback, and at that 90% fill factor, you have some decisions to make. Your operator has discretion. At 90% fill factor, you can just leave the 4 buckets that you match it to, come out with 180 tons. Another argument, you put a full 5th pass on there half the time, it'll balance out on an average, you're getting your payload on your truck. The problem with that is you're overloading some of the trucks, and if it takes the same amount of time to get that 5th heaping pass, you're not actually improving your productivity rate. The other one we see often, you put a 4th pass on there, you see 180 tons on the scoreboard, you decide it needs a little light top-off pass, right? If you're doing that, you may think it's fast because you're not spending a lot of time in the bank, but you can't reduce the swing time of your pass. So you're just wasting time overall. You're getting your payload, but you're taking it with the trade-off of your cycle time. So you're hurting your productivity. Or you can approach it, go for 5 struck passes faster, and you'll end up with a much better productivity rate, getting that payload on there at the right cycle time. And again, the chart that Bob was talking about, 2 of the biggest areas, your cycle time and your payload, it's finding the balance between the 2. So from the loader's discretion, they can have the trend inside their cab and look at the last 10 loads in that material. They shouldn't wait until the 4th pass is on to determine if you need the 5th. You should go know the material, go into it with a plan to have that 5th pass and go faster on all 5. From an operator management, your training management, pit supervisor type of position, you should be looking at the dashboards, trending this machine data over time, your payloads. People respect what you inspect, not what you expect. So sometimes just knowing that you're correlating the payload to the shovel's distance to the face will get the operator to focus more on moving closer to the face without even being instructed to. So that's measure everything, have a more specific action plan. You got to communicate what you want them to do and trend the results afterwards, and that'll help steer the right behavior. We'll get into a couple examples.
Here. This is an actual job study that we did over the last several years with one of our customers. If you look at the curve here, the load distribution curve on the left, you can see over the 3 years where they worked with payload management to move that whole load distribution curve over to the right. This shovel here is rated at loading 120 tons per pass. And you can see over time, they improved the underloads instead of sending trucks out, basically from the performance. Now this data here is coming actually off the shovel, not the trucks. And that's how they were achieving this with this one right here. And basically the goal of this is to switch the deviation, shift the mean, while still not exceeding the 10-10-20 policy on the trucks, which is pretty common across the board. But this is how a good example of how one customer really succeeded in improving the overall payload and performance of not only the shovel, but also the trucks. hopefully that we're getting a lower cost per ton too as well on that piece.
So these are some good results from a site in the oil sands. How they achieved that was implementing the technology, implementing the operator training, a few of the practices that we're going to talk about, and a few of the things that we talked about previously. So this is a chart of shovels in the oil sand, 2 shovels from 2015 and 2018, looking at the payload versus the cycle time. You spend more time in the bank, you increase the payload of the bucket to a certain point. Then it plateaus, you have diminishing returns after the vertical line there. So on the left side, we can quantify the trend line and say for every 8% fill factor that we reduce, you save 10 seconds in your cycle time. And this goes back to helping you determine whether you want to strategize for the 5 struck or the 4 heaping, in this case, 3 or 4. After that 50 seconds, everything beyond there may be opportunities for condition monitoring, or sorry, material conditioning, a little more support equipment, some of those other things we talked about that are the prerequisites. Another example from the oil sands, same shovels, 2015 and 2018. This is looking at your crowd displacement. This is a representation of how close the shovel is to the face. If you're reaching way out there, you have less digging force, less payload, longer cycle times, more machine wear. Starting closer to the face equals larger payloads. And these are just some of the things that you can be looking at from that machine data. All the data is out there. You want to download it, analyze it, measure it, have a good action plan. So in conclusion, a few of the takeaways: you got to look for the bigger missed opportunities first. Look at your cycle times and your machine configuration. Consider a scale study to go back and verify those densities. Operators can use the technology systems, the real-time feedback to fine-tune their discretion. It's just important to not expect it to think for you, tell you whether you need the 5th pass. Managers can continuously analyze using the performance trending systems. It's important to measure your success, have that actionable plan. It's also important to consult with mining experts, benchmark within your company and externally, so that you can define your metrics and targets and refine them as you go. It's an iterative process. So download the data, try a few new metrics. These are just a few we showed you. You could also look at like your average swing angle. When we go do a production study, we look at dozens. All this data is out there, it's available to you. If you don't know where to find it, if you don't know how to interpret it, please reach out. We can definitely help you with that. And remember, people respect what you inspect, not what you expect. Any questions? Yep.
Have you been able to quantify the benefits in terms of dollars or percentage of operating costs by achieving full truck rates?
We can quantify the potential and increase production, and then you would have to go back and validate that. There's a lot of interdependent systems. So improving your payload on the truck decreases your cycle time, a lot of downstream effects, right? And through the processing and everything. So you really need to validate it, make sure that it's not affecting some other system, and have that holistic approach. Being a little too narrow in your focus of saying you can improve this doesn't actually come out with the same results. So validating is a very important step in change management.
Mm-hmm.
Good question, though. Thank you. Does that answer it, Corey?
Yeah.
Okay. Thank you.
Not as simple as one would hope.
No.
Certainly. A little oversimplified approach, yeah. I haven't personally. I think
I haven't either, not with underground.
surface specifically, but I
Yeah.
think it's definitely possible, right? There is machine data out there. There's certainly resources to do the production studies and everything. I haven't personally. Right? Sorry. Yes. Either one?
Either one.
Go for it.
On your cost model, have you looked at that cost model by
It's just a generic information we learn across the board. We validate it with some customers, but some mines it might be a little higher, a little lower, but generally the percentages are relatively close. Depending on truck size, and it's kind of encompassing a wide range of trucks and equipment. So we just kind of put that in there. So and if you can relate to it, hopefully it's directionally correct. Haulage is a big piece. I mean, everybody knows that because they've got more trucks than got anything else. So obviously, it should be one of the bigger costs.
So the question was, you had that slide about the 200-ton truck, 50-ton shovel bucket, where you came down from that 100%. So I couldn't get that right. At the end of the day, you're recommending that 80% fill factor with 5 passes is being more efficient. Was that the conclusion?
So in that case, if you can improve your cycle time, reduce it enough to be beneficial. And if we go back, it was not even faster. It was comparing 128 seconds to 130. So it wasn't faster, but it was more beneficial. So it's really weighing between the cycle time and the payload. I don't know, did that answer your question?
Yeah, yes, but I mean, to achieve that, I understand that. So thanks for that clarification. But you need to have payload system in the shovel or get feedback from the truck.
Something.
Right?
Yeah.
Certainly.
Otherwise, I mean, getting 80% 5 times better.
Exactly.
Yeah. And to that comment, though, if you look at the third line where it says 200 tons times 149 seconds, we see a lot of that. You got to look at the time. What the saying is that you can do 5 in less time to equal the one on the engineered system solution. But typically, what we see is the one in the third. We're taking the extra pass to top off the truck for the payload, and at the expense of the loader. So, I mean, the whole theme here is to go back to the operations, take a look and see, am I getting the value that we invested in that loading pass match from the engineered solution? Okay, does that help better?
Yeah.
Okay.
Yeah, great questions. Any others? Go ahead.
Good. You have a slide about bucket size and increasing bucket size. At what point, what point do you say, okay, well, yeah, we can increase it a little bit, and at what point do you say, okay, well, we've increased it too much, we're now putting too much strain on the machine that's not designed to have in the first place? Where's the balance?
Certainly. It's good to be conservative, and when we're talking about the range of densities and the different materials you get into, you really have to spec it for the high end of the range and also be productive at the low end. And if it's a big enough range, sometimes it's a different loading tool or different trucks for different materials allocated to different areas, right? I don't know, did that answer your question?
Yeah, and then the other piece to that, all the OEMs, all these loading tools have a ready suspended load. So as you're increasing and maximizing that, you want to check in and make sure that you're not going too far, and you can get that technical help to help with that decision. Yeah, I mean the shovels have the same feel the same effects as trucks. Everybody's really familiar with the 10-10-20 rule, but the shovel also feels the same thing too as well. The load distribution curve applies to it as equally. Yeah, good question.
Any other questions? Danny?
Well, it depends on where you're going to start from. If you've got an older machine that's sized at one size, and now you want to upsize that, you're already experiencing life. So there's so many factors that go into that machine, fatigue, age, and all that, and where you're at in your rebuild cycle and component replacement. So that's kind of a hard question to answer. We know that on an older machine, and you suddenly start upsizing it, you're probably going to see some lower component life. So it may increase your maintenance costs.
Question relating to the truck and autonomous truck. If the truck is autonomous, will anything change?
No.
You have a lot of these spots.
Yeah.
Say again? A lot of
Your motor can set it every time, so it'd be a lot easier to hit that. Well, you go exactly where the motor operator is supposed to. So they can have lock control, centering that way, and that way over there. And also respawn.
When you look at the truck shovel interaction, truck spotting and queue time is probably the single biggest factor that affects the performance of the shovel of all those three. So with the autonomous, the truck is going to get in there quicker, depending on what's going on.
Quicker, and as he was saying, the position of it's going to be accurate. So if your crowd position of over the truck is from the face having to extend out or come in to be centered over the truck, that increases your cycle time as well. So having that truck in the perfect spot, centered loads every time, you're swinging optimally and getting a faster cycle time out of it.
And also you pay the lots, so you save the lots on that truck. Doesn't need the loader operator to be positioned in the spot. It's not another song on it.
Okay. Good questions.
Yeah, excellent.
All right. More?
I just, my comment is, I would love the shovel to be autonomous too, so, because, I mean, okay, that one spotting and all that.
Yeah.
Is, you would achieve it with both of them having purposes in that maximization.
Exactly.
And honestly, I don't know, I haven't been a shovel operator, but to me, the whole day going like that and leaving and under a lot of shock and vibration, that can be good.
Depends.
Side.
Okay. Any others? Thank you.
Yeah, we really appreciate everyone sticking around.